You know, when we look at ancient ruins, like, say, a stone foundation of a building, there's this overwhelming sense of finality to it.
Right. Yeah. It's done being built.
Exactly. It's just sitting there resisting gravity and, well, waiting until it eventually crumbles.
I mean, it is the ultimate monument to passive architecture.
And for almost all of human medical history, that is exactly how we viewed our own internal foundation, the human skeleton.
Which is wild to think about now.
It is. So today, we are taking a deep dive into the source material you sent us. We've got your stack of articles, the research papers, your personal anatomy and physiology notes.
That's a lot of material, yeah.
It is. But our mission today is to completely dismantle that passive static idea. We are focusing specifically on bone structure to show you that your skeleton is, well, it's not just a rigid frame holding you up.
No, not at all. But that misconception is so deeply rooted, it's actually baked into our language itself.
Oh, right, the etymology.
Yeah. So the word skeleton originates from the ancient Greek word skeletos, which literally translates to dried up or...
Desiccated.
Exactly. Desiccated.
It's just this linguistic fossil that perfectly captures, like, the oldest medical misunderstanding in history.
The idea that bone is just this dry, inert scaffold, keeping your soft tissues from just, collapsing onto the floor.
Right. And to understand just how spectacularly wrong those ancient physicians were, we have to track how the scientific definition of bone has undergone these two massive reality-bending shifts.
Yeah, and the first one hits right in the 19th century.
When they finally got good microscopes, right?
Precisely. Microscopists and physiologists finally look closely and realize, wait, bone isn't a calcium rock?
It's alive.
It is packed with living cells. It has a massive blood supply, and it actively remodels itself in response to mechanical loads.
So it's dynamic architecture being built and rebuilt continuously.
Huge leap from a dried-up scaffold. But the second shift, that's what completely changes the game.
Yes. Okay, based on your research notes from the mid-2000s, there was this team of endocrinologists led by Gerard Carcenti at Columbia University.
Right.
And they made a discovery that just flipped the whole field on its head. Bone isn't just responding to the rest of the body, right?
No, it is actively sending out commands.
Which is mind-blowing.
It really is. Carcenti's team demonstrated that bone cells secrete this specific hormone called osteocalcin.
Okay.
And once it's released, this hormone travels out of the bone, enters the bloodstream, and directly influences insulin secretion in the pancreas.
Wait, really?
Yeah, and it affects how other tissues process glucose, too.
Okay, wait, so you're telling me my femur is acting like some kind of slow-motion pancreas?
Well, yeah, I mean, the femur is absolutely participating in metabolic regulation.
That is insane.
Right. Finding a bone hormone that controls blood sugar completely ran against decades of established textbook biology.
Because everyone assumed that job belonged strictly to the pancreas, the liver, and fat tissue.
Exactly. So suddenly, the definition of bone expands from this living structural tissue to a bona fide endocrine organ.
Which, okay, that raises a flag for me when looking at the clinical data in our sources.
Oh, about the human trials.
Yeah, because Carcenti proved this mechanism beautifully in mouse models. But the clinical relevance in humans seems to be, well, fiercely debated among diabetes researchers.
And that's fair. I mean, humans are not just scaled-up mice.
Right.
We always have to apply that critical lens. A physiological mechanism proven in an animal model does not automatically transfer cleanly to human biology.
Because our bodies work differently.
Yeah. In mice, the osteocalcin pathway shows dramatic control over glucose metabolism. But replicating those exact profound metabolic effects in humans, it's been complicated.
Because of our metabolism.
That and the fact that we have bipedal locomotion and our bone turnover rates are vastly different from a mouse.
Ah, right. We walk on two legs, so our bones are under totally different stresses.
Exactly. So the debate really centers on how dominant this bone-to-pancreas signaling is in our daily human physiology.
But I mean, regardless of where the specific human clinical trials land, the discovery itself alters what we think a skeleton is actually for, right?
Oh, 100%. It proves your skeleton is participating in the biochemical conversation of your entire body.
So to understand how a seemingly solid, rock-hard object can act as a metabolically active organ, we have to, zoom in on the two distinct architectural styles the body uses to construct it.
Right. So when people picture a bone, they're usually picturing compact bone.
Also known as cortical bone.
Yes, that is the dense, solid-looking outer wall of every bone in your body.
Like the shaft of your arm or leg bone.
Exactly. It makes up the entire shaft, the diaphysis of your long bones, like the humerus or the femur. And overall, it accounts for roughly 80% of your adult skeletal mass.
But then, tucked inside the ends of those long bones, the epiphyses, and sandwiched inside flat bones like your skull, is the remaining 20%.
Right, the spongy bone.
Or trabecular bone, technically. And I just have to say, spongy is such a misleading name
It really is.
because it implies it's soft, like a kitchen sponge.
Yeah, people hear spongy and think squishy.
Yeah.
But trabecular bone is actually a honeycomb-like network of incredibly rigid bony struts.
The sources use a fantastic analogy here, actually. It's engineered like a truss bridge.
Oh yeah, that's a great way to visualize it.
It's designed to provide maximum compressive strength while using the absolute minimum amount of material.
Which is crucial, because if your bones were 100% solid compact bone all the way through, your skeleton would be so incredibly heavy.
You wouldn't even have the muscle mass to stand up.
Exactly. The trabecular lattice balances structural strength against weight.
Okay, but I have a question about this. If this spongy bone is so brilliantly engineered, why is it the first place we see catastrophic bone loss in diseases like osteoporosis?
Ah. Well, the answer to that comes down to geometry and surface area.
Okay, how so?
Think about a solid block of ice versus a glass of crushed ice.
Yeah.
The crushed ice melts much faster in the ambient air, right? Because exponentially more of its surface is exposed.
Oh, I see where you're going with this.
Yeah, so spongy bone, being a 3D lattice, has vastly more exposed surface area than a solid block of compact bone of the exact same volume.
Right, and because bone is a living tissue, all that surface area makes it a hyperactive site for metabolic exchange.
Exactly. The body essentially uses the skeleton as a daily calcium bank, making withdrawals and deposits all the time.
And the tellers at that bank are three major regulators, right? Parathyroid hormone, calcitonin, and vitamin D.
You got it. To put it simply, when calcium levels in your blood drop, parathyroid hormone is released.
So that acts like a withdrawal slip.
Yes. It stimulates the bone-dissolving cells to break down the matrix and release calcium into the blood.
And then calcitonin does the reverse.
Right. Calcitonin acts like a deposit slip. It inhibits those dissolving cells when blood calcium is high, allowing the bone builders to store the excess.
And vitamin D is the middleman.
The crucial middleman. It chemically ensures your gut can actually absorb calcium from your diet in the first place to, supply the bank.
Got it. So because spongy bone has so much exposed surface, these hormonal regulators can access its calcium stores way faster than the dense compact bone.
Exactly. So when a disease like osteoporosis accelerates those calcium withdrawals, the spongy bone gets depleted first, simply because it is the most accessible account.
It's the checking account, not the CD.
Exactly. And we see a highly clinical historical example of this in the neck of the femur.
The thigh bone.
Yeah. In the 1830s, a British anatomist named F.O. Ward mapped out this naturally sparse, roughly triangular region of trabecular bone in the upper thigh bone.
Which is known today as Ward's triangle.
Right. It naturally has fewer, thinner struts because that specific spot experiences lower mechanical stress during normal standing and walking.
But clinically, because it starts out sparse and has that massive surface area for calcium withdrawal,
Yep.
Ward's triangle must be where osteoporotic bone loss becomes visible the earliest on an X-ray.
You see it there first. And it perfectly explains why the hip is such a devastating and common fracture site in elderly patients.
Wow, because it becomes structurally compromised very quickly once those withdrawals outpace the deposits.
Exactly. But, this high-speed metabolic exchange and the structural remodeling happening in the bone, it isn't magic.
No, it's orchestrated by a microscopic plumbing and sensory network hidden right inside the hard matrix.
Yes, and mapping this hidden city started way back in 1691.
Oh, with Clopton Havers.
Yes, the English anatomist. He published a text called Osteologia Nova.
Right.
He was looking at compact bone through early microscopes, and he described these tiny cylindrical channels running straight through the dense bone, carrying blood vessels.
And we still call them Haversian canals today.
We do.
So the fundamental structural unit of compact bone is the osteon, or Haversian system.
Yes.
I'm picturing it like a microscopic tree trunk, right?
Yeah.
The Haversian canal is the hollow center carrying the blood supply, and surrounding it are these concentric rings of hard bone matrix called lamellae.
Just like tree rings.
Yeah.
And running perpendicular to those central canals are Volkmann's canals, which connect one tree trunk's blood supply to the next.
So it's this vast 3D plumbing system threading through solid rock.
It really is.
The plumbing is fascinating, but honestly, the residents living inside the rock are what really capture my attention.
The osteocytes.
Yeah, there are living bone cells, the osteocytes, sitting in these microscopic cavities between those tree rings.
Yep.
And because the hard mineralized matrix isn't permeable you can't just diffuse nutrients through it like you do in soft muscle tissue.
No, you can't.
These cells must have to pass nutrients and waste to each other like a microscopic bucket brigade.
They do exactly that to survive. The osteocytes are connected by a vast network of infinitesimally small channels called canaliculi.
Canaliculi.
Yeah. The cells literally extend tiny molecular arms through these channels, touch their neighbors, and pass that bucket of nutrients down the line in a relay.
All the way from the central blood vessel out to the distant edge of the osteon.
It's incredible.
It is. But wait, if these osteocytes are walled into a microscopic mineral cave their entire lives, how do they sense anything happening outside?
That is the million-dollar question.
Right. How do they know when to tell the rest of the body to remodel the bone?
So this puzzle was solved by a biomechanics researcher named Lance Lanyon in the 1980s.
Okay, what did he find?
He established that osteocytes are highly sensitive mechanosensors.
Meaning they feel mechanical stress.
Yes.
Oh, yeah.
Those tiny canaliculi channels, your bucket brigade, they aren't just empty tunnels. They're filled with fluid.
Oh.
So when a bone bends or takes on a heavy load, the fluid inside those tiny channels shifts. It gets squeezed.
Ah. So as it moves, it creates shear stress against the membranes of the osteocyte cells.
Exactly. The cell physically feels the fluid rushing past it.
Wow.
And the osteocyte then translates that physical fluid movement into a biochemical signal.
Okay, how?
Specifically, they regulate a protein called sclerostin. In a resting state, sclerostin suppresses bone formation. It keeps the building cells inactive.
But when the osteocytes feel that fluid shear stress from a heavy mechanical load?
They dial the sclerostin down, they turn off the suppressor, and signal the construction crew to start building.
And the construction crew being the osteoblasts, right?
Right, the cells that secrete fresh, unmineralized organic matrix that later hardens.
So the demolishers, the osteoclasts, must be working alongside them to clear the old material first.
Yes. In healthy adult bone, they work in tightly coupled teams called basic multicellular units, or BMUs.
BMUs.
Right. And orthopedic researcher Harold Frost proposed a concept called the mechanostat theory to explain this teamwork.
Like a thermostat.
Exactly like a thermostat in your house. If mechanical strain goes up, it triggers the addition of bone mass. If strain goes down, it removes mass to keep the physical strain near a genetically set baseline.
That is so elegant. And this cellular mechanosensing is the engine behind one of the most famous laws in human anatomy, right? Wolff's Law.
Oh, yeah. Julius Wolff, a German surgeon, published his defining work in 1892. By studying sawed sections of cadaver bones, he realized the internal trabecular struts beautifully align with the specific lines of mechanical stress the bone experiences during standing and walking.
So basically, bone adds mass where it is mechanically loaded and dissolves mass where it is idle.
It is the ultimate biological expression of use it or lose it.
And based on the NASA spaceflight data in our sources, this law goes to extreme lengths in microgravity.
Oh, absolutely. When astronauts live aboard the International Space Station, the constant mechanical load of fighting Earth's gravity disappears entirely.
Guess they're floating.
Right, so the billions of osteocytes sense that drop in strain immediately because the fluid stops shifting in their microscopic channels.
The mechanostat registers the drop in stress.
Yep. The osteoclast demolition crew goes into overdrive, and the body begins dismantling a skeleton it no longer thinks it needs.
The sources say astronauts can lose 1% of their bone mass per month.
Per month, yeah. And it's heavily concentrated in the load-bearing hips and lower spine.
To put that in perspective, a postmenopausal woman with osteoporosis here on Earth might lose roughly 1% of her bone mass per year.
Yeah, spaceflight is a whole-body, accelerated demonstration of Wolff's Law.
But that makes me wonder, if this smart biological programming can ever get tricked.
Tricked how?
Well, we design medical interventions to fix bones constantly, right? Can Wolff's Law backfire on us if we change the mechanical environment too drastically?
Yes.
Yeah.
Big time. It has actually caused one of the most significant hurdles in the history of orthopedic surgery.
Oh, really?
Yeah, it's a phenomenon known as stress shielding.
Stress shielding. Okay.
So in the 1970s and 80s, engineers designed early metal hip replacement stems to be as rigid and unyielding as possible. They implanted them deep into the femur.
I think I see the problem. If the rigid metal is taking all the mechanical load of walking,
Yep,
the natural bones surrounding the implant isn't experiencing any stress,
exactly. The osteocytes stop feeling the fluid shift.
which means the sclerostin levels go up, the osteoclasts activate, and the natural bone senses it's obsolete.
It literally dissolves its own foundation.
Wow. The metal shielded the bone from the stress, so the bone melted away.
And that caused those early implants to loosen and catastrophically fail.
So how did they fix it?
Implant engineers had to completely rethink their approach. They deliberately redesigned stems using more flexible materials and geometries,
Like what?
like titanium alloys with specialized porous coatings. The goal is to closely match the natural stiffness of human bone.
So that ensures the mechanical load is shared, and the surrounding bone still feels enough stress to maintain its mass.
Exactly. But biology is a messy reactive system.
Right.
Wolff originally claimed in his trajectorial theory that trabecular struts align precisely along mathematically calculated stress trajectories.
Almost like the bone was perfectly solving a physics equation.
Right. But modern finite element modeling shows that while the correlation is incredibly strong, bone shape is also constrained by developmental patterning, genetics, and blood supply.
It's not just pure math.
No, it's not. And all of this dynamic adaptability ultimately relies on the physical materials the bone is actually constructed from.
Which brings us to, I think, the most common misunderstanding about bone health.
Oh, the calcium myth.
Exactly. If you ask a random person what makes bones strong, they will almost universally say calcium.
And the sources make it very clear we need to completely dismantle that myth.
Because bone is a composite material, right?
Yes, about 2/3 of it is inorganic, a crystalline calcium phosphate called hydroxyapatite.
And that mineral gives bone its compressive crush strength.
Right, but the remaining 1/3 is organic material, mostly a protein called type I collagen.
And the collagen gives bone its tensile strength and flexibility.
Exactly. Think of how we build skyscrapers.
It's exactly like reinforced concrete. The calcium is the concrete. It stops the building from crushing downward under its own weight.
Right.
But concrete on its own is notoriously brittle, so you need the collagen to act as the flexible steel rebar hidden inside.
Because the rebar stops the structure from snapping in high winds or under twisting forces.
Exactly. And we see the profound reality of this dual material system in human pathologies, don't we?
We do. If a patient has a genetic collagen disorder, meaning they have the mineral concrete but lack the steel rebar,
Right.
their bones become incredibly brittle and shatter under minor impacts, like in osteogenesis imperfecta.
So if the collagen rebar prevents shattering, losing the calcium must mean the bones lose their rigidity and just like fold under gravity.
Unfortunately, yes. If someone lacks calcium or the vitamin D required to absorb it, leading to diseases like osteomalacia or rickets.
They have the flexible rebar but no solid concrete.
Exactly. Their bones become pathologically soft and literally bow and bend under the weight of their own body.
Wow. So bone strength is not a single ingredient property. It is a composite material property.
And understanding this architecture, the macro, the micro, the materials, it shapes exactly how we interpret bone density scans to estimate fracture risk.
It also reinforces why doctors universally prescribe weight-bearing exercise to age gracefully.
Exactly. You have to trigger those osteocytes and make the fluid move to maintain density.
And, moving beyond medicine, this knowledge is heavily utilized in forensic and archaeological science, too.
Oh, definitely.
Because spongy bone remodels faster than compact bone, and because the osteons leave behind specific microscopic scarring patterns as they are continually rebuilt by those BMUs.
Yeah.
Scientists can estimate a person's age at death purely from a cross-section of their skeleton.
They can even reconstruct their lifestyle. A medieval blacksmith, for example, will have drastically different stress patterns, thicker cortical walls, and distinct trabecular density in their dominant arm.
Compared to someone who, say, performed light agricultural work.
Exactly. And it is all perfectly recorded in their bone architecture.
That is just incredible. So let's look at what we've unpacked today. We started with an ancient linguistic fossil, the idea of a dried up, inert scaffold.
Right.
And we've completely replaced it with a modern understanding of a highly dynamic, hormone-secreting, structurally optimized living organ.
A living structure that continuously shapes itself to the exact physical demands you place upon it.
It remodels itself using microscopic fluid sensors, balancing the rigid strength of calcium with the flexible resilience of collagen.
It really is an engineering marvel.
Yeah, it is. Which brings us to one final implication of Wolff's Law for you to ponder after we wrap up this deep dive.
Oh, this is a good one.
Your skeleton is an active, living diary. It continuously remodels its trabecular struts and compact shafts based on the specific mechanical loads you subject it to every single day.
The mechanostat is always running.
Always. So ask yourself, if bone adds mass where it is stressed and dissolves it where it is idle, what exact shape is your modern lifestyle like? Sitting at a desk for 8 hours, craning your neck downward to look at a phone. What is that permanently carving into your bone architecture right now?
That's a terrifying but very real thought.
It really is. Next time you think of a skeleton, remember the ancient Greeks were wrong. It is not a dried-up relic of the past. It is the ever-changing shape of your present.